Hi guys, I'm back, and this time we're going to talk about soil pH and soil salinity. Those are topics for the week, so more about soil chemistry. And let me get the slide up so we can go through this. Okay. All right, so first of all, we have measured soil pH before, and we've talked about soil being acidic or soil being basic, but we haven't really gone into the chemistry of what those terms actually mean. So the way that we measure if a soil is acidic or basic is that we measure its pH, which is likely a term you've heard about before. You've definitely heard about it in this class. And pH means puissance de hydrogen, which I'm sure I'm pronouncing wrong. That's French. But basically that means what is the strength of the hydrogen, or how many hydrogen ions are in the soil. So the higher the number of hydrogen ions, and now this is a little bit confusing, the higher the number of hydrogen ions, the lower the pH of the soil is. So if you have a really low pH, that means you're very, very acidic. So something like hydrochloric acid or stomach acid has a very, very low pH, and that's because there is an enormous number of hydrogen ions, and they happen to be cations or positively charged ions in the soil. So that's a low pH. A neutral pH is around 7. And then a high pH can go all the way up to 14. And so other things like ammonia or bleach are very basic. And then, of course, there's a lot of things in between. Some things are slightly acid, certain vegetables, seawater or baking soda or eggs would be slightly basic. But they all have a ranking on this scale from 0 to 14, with 1 being no excess of hydrogen ions above hydroxyl ions, OH ions. So that would be like pure water. And then lower being extra, more and more and more hydrogen ions. And then the other side, higher values being fewer and fewer hydrogen ions. So that's basically what it means when you get a pH ranking. Okay, so why do we care about the pH? Well, one of the most important things about the pH is that it influences the ability for plants and other microorganisms to access nutrients, which again, remember, just different kinds of chemical compounds that are in the soil. So I'm going to have us for a few minutes look at this diagram that I have on the bottom of the slide here. And basically, there's a bunch of different nutrients that are listed along the right-hand side. So like nitrogen, phosphorus, potassium, calcium, magnesium, etc. And then along the top, there is different soil pHs. So remember, 7 is a neutral pH. And then lower than that is acidic. Higher than that is basic. Okay. And then you can see for each of these nutrients, there's a bar. And the width of the bar indicates basically how many available elements of that type, or how many nutrients of that type would be accessible to plants that are growing. And you can see that the width depends on the pH, right? So nitrogen has a wide band in neutral pH zone, and as we get acidic, kind of beyond a 5 pH for acidity, or basic above a 9.0 pH, we would start to have decreased access to nitrogen. So other nutrients are different, but they all are influenced by the pH in the soil. So I'm going to give you guys a minute, and I'm going to ask you guys to look at this diagram and think about some nutrients that might be available well in the acidic soil, but not available in basic soil, and vice versa. A couple nutrients that seem to be well established or available in basic soils and not available in acidic soils. So you can pause for a minute and check out, kind of interpret this diagram. Okay, so now that you've had a moment to do that, I've kind of given you a head start by circling some of these areas. But basically on the left-hand side, towards the top, we can see that a number of elements like potassium, calcium, magnesium, sulfur, phosphorus, also nitrogen, start to get quite a bit more narrow in the kind of acidic end of the spectrum. So highly acid soils are going to be difficult for plants to grow in if they are needing these particular nutrients. And then on the other hand, certain elements like aluminum, boron, copper, and zinc are really more limited in the areas of pH that are more basic. And then we saw that nitrogen kind of tapers off at both ends of the spectrum. Also, actinomycetes, certain kinds of fungi, are listed kind of in the bottom range of this graph as well. And you can see that in highly acid soils, we would start to lose out on certain kinds of soil fungi that we know have a lot of important soil roles. So the slide I originally said, why do we care about pH? Well, we care because it influences the uptake and availability of nutrients. It also influences the mobility of those nutrients, so how they can move around. And again, some of those nutrients can be toxic, so it might influence the toxicity of the soil. And then also now we're adding the fact that there's an importance in microorganism activity that could be associated with soil pH as well. Okay, so then we want to think about this is why we care. Now, what are the factors that might influence the pH that a soil has? So the first thing is climate and rain in particular. So as rainwater comes down from the sky, it reacts with certain compounds like carbon dioxide, like NOx gases, nitrogen, oxygen compounds, sulfur dioxide, and it creates different kinds of acids. So carbonic acid when it combines with carbon dioxide, sulfuric acid when it combines with sulfur dioxide, nitric acid when it combines with these different NOx compounds. And all of those are acids, and they have hydrogens in them. And then in the soil environment and in the soil water environment, those hydrogens can disassociate from the acid compound and can act as these hydrogen ion actors in the soil. And that's where a soil might get its acidity from. So the more rainwater we have, the more hydrogen ions we're going to be introducing into our soil matrix. And then in addition, rainwater has another influence, which is that it can actually rinse out other kinds of basic cations that might counteract the hydrogen ions in the soil by bonding on to the negatively charged soil colloids that we talked about last week. So if we have a lot of things like calcium and magnesium and potassium, remember these can bond onto the soil surfaces. But if we have a whole bunch of rainwater coming in, the rainwater might grab onto those base cations and wash them through the soil profile. So get rid of those base creating ions and then replace them with these hydrogen ions instead. So again, the more rain we have, the more acid or lower pH value our soil is likely to have. So here's some maps of the United States. And so you can see, or hopefully you can read, that the top map is showing soil pH in kind of North America and some of South America as well. So dark red is strongly acid, white is neutral, and then blue is getting into a basic or alkaline soil type. And so you can look at this and kind of identify some places that you might be able to go to find acidic soils. So I'll give you a minute to do that. You can pause if you need to. And then also think about places where we might have basic soils. Okay, so to check in places that are rainier, so places like Seattle or Vancouver, places like the East Coast that are more humid and rainy, are going to have more acidic soils, and then areas in the kind of intermountain west and the southwest, which we know are kind of the desert regions of our country, those are going to have more basic or alkaline soils. And then on the bottom here, I have a map of rain. So you can see that on the rain map, the yellow areas are the dry areas, and the blue and green areas are the rainier areas. And so the lower map, where the yellow areas are showing dry, those correspond to the same areas that are blue on the upper map, indicating basic or alkaline soils. And then the areas that are blue and green on the rain map correspond to the red areas or the acidic areas on the top map. And then we can see the Rocky Mountains kind of coming down in both maps, where it's a little bit rainier higher up in the mountains, and therefore a little bit more acidic soil conditions up in the mountains compared to the kind of like high desert area and desert area, plains areas around that. So those are the kinds of patterns that we would expect to see for soil pH. Other things can contribute to soil acidity, and that another important element is the amount of organic matter. So a lot of organic compounds have hydrogen in them. Different kinds of organic acids would, by definition, have these hydrogen compounds that define an acid. So if you have a lot of organic matter, you're going to more likely have a lower pH, and certain kinds of plants do better in that environment. Things like berries or rhododendrons are going to be loving this acid soil, whereas other kinds of plants, lettuce, cabbage, is not going to be loving quite as much acidity in the soil. The other thing about organic matter is it forms different kinds of soluble complexes with base cations. So basically what that means is that it bonds to things like the calcium and the magnesium in the soil, and then they are no longer, those cations are no longer grabbing onto the soil colloids, but instead they're grabbing onto the organic matter and then getting potentially flushed or washed out of the soil. So that's another thing that can leave behind a more acidic condition. And then the final thing, aluminum, the presence of aluminum is important. So aluminum is a cation as well. It has a 3+ charge compared to most of the other cations that we've talked about that have a 1+ charge, like hydrogen or potassium, or a 2+ charge like calcium or magnesium. And aluminum is particularly influential in soil pH because it is what's called hydrolyzing, which means it has a strong enough power, essentially, that it can break apart water molecules to create hydrogen ions and hydroxyl ions. So it can break apart the water into an H piece and an OH piece. And the H piece, again, is basically what creates soil acidity. So the more of these H's that we're releasing into the soil, then the more acid our soil is going to be. And also aluminum with a 3+ charge can kind of take up 3 times as much negative charge, or balance out 3 times as much negative charge on the soil surface. And so it's going to be kind of kicking off more potential hydrogens to be moving around in the soil. Okay, so aluminum is something that is of grave concern. One, because it, as we already said, can make a soil very acid to an extent that might be difficult for the plants to have proper nutrient uptake and have proper fungal growth in the soil. And as the pH gets lower and lower, maybe below like a pH of 5, the aluminum gets into the soil water and starts to create problems. So we'll see lots and lots and lots more aluminum below a pH 5. And when aluminum is around, it starts to be uptaken, absorbed into the roots of plants. It doesn't have an important nutrient function, and instead it damages membranes, it interferes with energy production, and it interferes with potential DNA production in plants. So on the right here, I have a picture of root growth of cotton plants in different soil conditions. So soil 6.5, very slightly acid, and then pH 5.2 and pH 5.5, and you can see that the root growth is much lower or much less in these pH conditions. And then on the top, you can kind of look at the plant health, and unfortunately it's a little bit hard to see in this particular picture, but basically the plants that are looking less healthy are growing in soils that have higher aluminum and lower pH values. So experiencing this aluminum toxicity phenomenon. Okay, so on the other hand, we might have other conditions that would create basic or alkaline soil. And so one of those things is that as silicate minerals, right, which are these kind of mineral compounds that exist in the parent material or rocks, weather and break apart, they can start to bond with hydrogen ions in the soil. And as these hydrogen ions are bonding to the silicate compounds, they're not moving around in the soil, and so they're kind of taken out of commission and they're not influencing soil pH anymore. So that's one thing. Another thing is the more what we call base cations, or these non-hydrolyzing, non-acid cations in the soil there are, then they can kind of compete with hydrogen ions for space on the soil matrix and in the soil environment. And so the more of these that are around, the less hydrogen is going to be accumulating in the soil environment. So where we have a lower overall rainfall, these base cations are not going to be leached or washed out from the soil. So again, these are things like calcium or magnesium, and they're going to build up in the soil when there's not a factor like rainwater that's washing them out. And then the production of base producing anions, hydrolyzing anions, and again, this is some terms that are kind of a little bit beyond of what we've talked about, but if we have things like carbonates in the soil, bicarbonates in the soil, and these could be things that are breaking apart from different minerals in the soil, especially like limestone types of rocks. These could be bonding onto the hydrogens in the soil and then releasing the OH hydroxyl groups, and therefore kind of tipping the balance away from hydrogen ions in the soil, which is by definition what makes soils acidic. So if we have these negative groups that can bond on to the positive hydrogen groups that can break down from water, then we're going to have a higher pH value, which again, somewhat confusingly means fewer hydrogen ions in the soil, and we call that like a basic or alkaline soil condition. And then another thing that happens is a lot of plants actually have root exudates that are bicarbonates. So there's certain rocks, parent materials, that have carbonate and bicarbonate in them, as I already mentioned, things like limestone, but there's a lot of plants that actually create these as well, and then they exude them, or they kind of spit them out through their roots as like a waste product, and then those are things that can be, again, bonding on and grabbing up these hydrogen ions so they're not moving around and influencing soil pH. Okay, so we mentioned this idea of base saturation last week. And remember that we said base saturation is basically the percentage of total cations that we can measure in the soil that are part of the base cation group, or group 1 from this particular slide. So how many of the total cations that we can strip off the soil colloid surface, and remember we mentioned we could do that by introducing some sort of acetate compound or something. We could see how many cations are there, and then of those we'd be interested to know which ones are calcium, magnesium, potassium, and sodium, because these are the elements that lead to the basic or alkaline conditions, as opposed to which of those cations that we're stripping off the soil are aluminum and hydrogen, which we have just discussed, like either by definition, because that's what it means to have a low pH, or in practice, because of their hydrolyzing capacity, the aluminum and hydrogen are going to lead to acidic conditions rather than basic conditions. And so we talked also about last week this idea of CEC, or cation exchange capacity. So we said the cation exchange capacity is looking at like how many cations can we strip off the soil surface, how many are there that are exchangeable. And in this case, base saturation is a more focused measurement that's similar, but is saying how many of those ions are going to be contributing to basic soil conditions or alkaline soil conditions rather than acidic soil conditions. Okay, so if we have a pH that we are not interested in, that's not desirable for a particular management objective we have of our soil, first of all, we might want to consider changing our management objective. Maybe we're trying to do something that's not appropriate for the landscape that we're in. So maybe we're trying to grow a type of crop that's not appropriate. So that's something to consider. But we can do certain kinds of things by adding amendments to shift soil pH somewhat. So if we want to increase our soil pH, which again means making it less acidic, more basic or alkaline, we can do things that are going to add these base cations to the soil. So we can add lime, or we can add gypsum. So that's calcium, calcium carbonate, calcium sulfate, essentially. And these things are both going to have components that could bond to hydrogens and release calcium in the soil. So those are both going to be activities that are going to increase our pH. If we want to decrease pH, we can try to add acid-forming organic compounds. Okay, so that could be like pine needles, pine sawdust, or peat moss. Or we can add aluminum, because we know that aluminum is an acid-forming material, and aluminum sulfate in particular is something that has aluminum and then dissociates into sulfuric acid. And so that's an amendment that's sometimes used in soil to decrease soil pH. Okay, so dry land soils, as we've already discussed, tend to be alkaline or basic in condition. And in this environment, these soils often have a high cation exchange capacity, right? They may have plenty of these cations around. They're not being flushed out by rainwater, but they still might have nutrient deficiencies. Certain kinds of nutrients might not be available, even if there's high cation exchange capacity. So I have this diagram that we looked at earlier on the right. And so if we have an alkaline soil, what kinds of elements might be in limited supply? Pause for a minute if you need. So things like nitrogen, things like boron, copper and zinc, iron and magnesium are going to potentially be lacking in a higher alkaline environment. So that's something to consider. And then also a little bit separate from pH, what's interesting about these dryland conditions is that as plants start to grow in these dry environments, they create little islands of fertility around themselves, where they actually kind of act as traps, and as wind is blowing like old leaves and other grass fragments or little pieces of poop or whatever around in the dry environment, the plants themselves act as traps. They trap this organic matter, and then the organic matter kind of breaks down into the soil and creates these little islands of fertility around the plants, where they start to have more nutrients, more organic acids, and so they start to shift the pH of the soil, but also just improve their overall nutrient and organic matter content and create these little fertile zones around plants. And so then we'll see other plants popping up in these fertility islands around plants that are already established. However, while this is interesting, it's also important to understand, because if we have some activity that comes in that takes out native vegetation and takes out these little fertility islands, and then the nutrients can be windblown and distributed around more evenly in the environment, maybe through overgrazing or through some other activity, then it's really difficult to reestablish plants in that area, because previously plants were establishing preferentially in these little fertility islands that have been broken down when native vegetation is removed. And again, often this happens as a result of overgrazing, although it could be for other reasons as well. So we want to be really careful about the way that we're managing these somewhat fragile dryland and often alkaline environments. Okay, so while we're on this topic, I'll mention salts as well. So first of all, when people think of salt, they often think of just table salt, sodium chloride, and that's only one type of salt. A salt is technically any chemical compound that's formed from the reaction of an acid with a base, with all or part of the hydrogen of the acid replaced by a metal or other cation. Okay, so instead of like hydrogen chloride, the hydrogen is released, so it can be doing its pH business, and then sodium is bonded on to the chlorine instead. So anyway, that's what a salt is. So there's lots of different salts in the environment besides just table salt. And there is a lot of sodium in the environment, so we have a special word that we use when we're describing salty soils that have a sodium salt component, and we call those sodic, as opposed to saline, which is a word that we use to refer to other kinds of salts that might be like magnesium chlorides or other, like potassium chlorides, other non-sodium salts. So sodic and saline, both in the salt realm, that have different meanings. Okay, so these salts are often natural. They originate from the weathering of different kinds of minerals, primary minerals that were in parent materials in the environment. However, over time in these dryland environments, as water, rainwater, or water that's washed in through surface water, or especially water that's pumped up and then distributed on the surface through groundwater irrigation, as that water evaporates, that water often contains these different kinds of minerals and salts in it, and the water can evaporate, but the salts can't. And so the salts are left behind on the surface, and they get more and more concentrated in these dryland environments over time. So the longer the environment has been sitting there, the saltier it is. In some cases, we have like ancient salt beds that might be exposed. And then we can think about these like modern salt beds, things like the Great Salt Lake area in Utah. And then there's a lot of these kind of salty lake bed environments all through the Intermountain West. If you think about like driving to Reno and seeing things like that big kind of playa in border town area, that would have a lot of salt accumulation. And as we already mentioned, when we're irrigating in these dryland areas, particularly if we're irrigating with groundwater that we're pumping up from the ground, so that ground has been sitting in contact with minerals, dissolving salts, and then we're spreading out that salty water on the surface in a hot environment where evaporation is happening readily and salts are being left behind, we can really exacerbate this problem. And then in some cases, we actually add salts to the environment on purpose, like for instance, to deal with frozen, icy road conditions, and that may also exacerbate the accumulation of salts in the environment as well. Okay, so why do we care about salts? Well, first of all, the more salts we have in the environment, the more base cations we have in the environment, because salts are made up of these base cations. And we have mentioned before that when we have pHs that are moving significantly away from 7, that neutral pH, we start to see nutrient deficiencies. So that's a problem. Another important thing is that we talked about earlier in the class, the osmotic potential as something that really drives water movement, where water is moving towards different kinds of salts or other things that are dissolved in water. And we said that the way that plants actually uptake water from the soil is they concentrate different kinds of base cations like sodium inside their plant root tips. And then the water moves by osmosis through the cell wall of the plant root and then towards the sodium. However, if we start to have a big buildup of things like sodium, magnesium, calcium, that are all part of salts outside in the soil, right outside the root, in excess of what's inside the root, it can really reverse that movement of water and make it impossible or very difficult for the plant to build up or uptake the adequate water that it needs to be able to grow. So it kind of breaks down root function. And here we have salt accumulation on a surface irrigated area in North Dakota, which is a relatively dry zone. And you can see that this is really quite prominent. There's all this white dust on the soil. That's not like an additive like gypsum. That's not snow. That's just like salt that's been accumulating here. And this is really devastating the ability of this particular landscape to continue to act as an agricultural location or as an agricultural resource. Okay, so what can we do to try to reverse the issues if we have too much salt in an area? Well, if it's saline, so remember that's not sodium based, we can try to improve drainage and try to flush the soil or like leach out the buildup of these salts. And we can do that by irrigating with clean, and this is usually going to be surface water. If we irrigate with groundwater, continue to irrigate with groundwater, we're going to continue to exacerbate the problem. So that's not always an accessible resource that people with saline buildup problems have. But if they do, they can start to try to flush for a number of months or years with surface water. They might be able to kind of wash out some of the saline buildup on the surface. On the other hand, if you have specifically a sodic buildup or sodium buildup issue, you might be able to try to correct this with the addition of calcium, which can help replace sodium in the soil. So compounds that we've talked about before, like gypsum, have calcium in them, which is why they're added to the soil for a variety of reasons. And this could be one of them. So the picture down here are farmers in northern India spreading gypsum on their soil. And in this particular case, it's with the objective of trying to rebalance a kind of sodium buildup in their soil. All right, that's it.